All right, great. I like to walk around. I don't like to be tied to a podium. This is the final talk. Thank you for attending part 3. I'd like to mention that we have a number of papers. We are in the process of getting the final versions of things, and we're going to get those reviewed. And hopefully by the beginning of next year, we will have an SP on these presentations. And there's also going to be some folks that prepared papers, but they were unable to come to the presentations today. So there might be some additional, you get some bonus papers, okay, on that. So this was actually kind of an interesting thing. So we're looking at headed stud anchors installed in the inside corner of an angle. I'm Neal Anderson. I work for Simpson, Gumpertz, and Heger in Chicago. Don Meinheit is I used to work with him at WJE. He's retired. And our third author on this is Susan Lasecki. She currently is a engineer up in upper Wisconsin, has her own firm. But interestingly enough, this is one of those things, oops. So this was based on the experimental work of Susan. She was a graduate student at the Milwaukee School of Engineering. She was getting her master's degree. And while she was doing this work, she was working, I believe, part-time for Spancrete, which is a precaster in the Milwaukee area. And she was looking for a project to do. And she was looking at a headed stud connection, and I'll show you here in a second what that is. But she was looking at doing some research on that. Milwaukee School of Engineering is more a teaching university, but she was going to do some experimental work. So she was consulting with a couple folks, Don Meinheit being one of them, and was consulting with Don on the project. And she did the project, finished her degree and everything, and this just sat as a master's thesis. It just sat and was growing mold and everything. So it never really saw the light of day. She never had time to prepare a paper, nor maybe she'd had any interest in it, okay? So I believe I had gotten involved in a project, and I was talking to Don. I said, hey, do you know anything about this? And Don's like, yeah, I remember working or consulting with somebody on this, and maybe there's something in there. So one thing led to another. I found Susan through LinkedIn, her current contact, and she sent me the thesis, and we got all the information. And you know, as we're putting together this symposium, it's like, you know, it'd be kind of nice for this to see the light of day, actually. Okay, so that's kind of where we're at. So it's kind of a serendipity approach here to how we got here. So what are we looking at? So basic outline. We'll give you the background. Experimental test results. Now this is all Susan's work. We're not trying to take credit for it, but we have kind of brought it into the modern, looking at CCD and also looking at some other things now that we're smarter here, or that now we're a little bit further along than 2007. Okay, we're going to look at the CCD approach and also perhaps look at a simplified design equation. So really, what are we talking about here? So if you look at some background, and this gets way, way back here, and this is back in the day. If you look at a Kahn was an engineer back at the turn of the century, in 1900s. There were the Kahn truss systems. They had reinforcing bars. He patented different types of floor systems, patented everything, okay? If you go to the web archive, you can get Kahn catalogs and what have you. And this happened to be one of his particular patented items, and this was a Kahn curb bar, okay? So there was a need way back when, back in the 1900s, to actually armor corners of concrete so they didn't chip off, like loading docks or something like that. Let's fast forward to the 60s when Nelson Stud Welding, they had come up with the stud welding, and there was a need to have some sort of an angle, but look at a 45-degree fillet or 45-degree angle on a stud, okay? Because maybe not your studs being normal to one of these surfaces didn't work all the time. So they developed a ferrule that they were able to shoot an angle or shoot the stud into the inside corner of the angle. So where else might you see this type of detail? Okay, so we talked about here armoring a corner right here, but you also see this a lot and this is kind of where the research came from Susan, and that was here. You had a precast plank, Spancrete in this case, and you're resting it on some sort of a concrete wall, either a precast wall, cast in place wall, or a tilt up, and you're putting an angle here just to protect that corner right there. Obviously you might be welding that up like shown here, or you're putting that on an elastomeric bearing pad. But in any case, you're here and you're protecting that corner, okay? Other applications that you might see, and I've seen this in the bridge work, where you might have an expansion joint and you're shooting the studs on either an angle here or some sort of a specialized stud or rail here where you're putting in the strip seal expansion joint, okay? And what really actually, and I didn't have a chance to draw it up at the time, but what I was seeing here is my particular case was something very similar to this, but this was a balcony edge where I had it was very thin. It was like about 6 inches thick, and the engineer had put very discrete angles here, okay, of a certain length, and they were putting the handrail here, okay? Because if you put a stud here or over on either side, you really weren't getting the capacity. So they were putting it at a 45-degree angle, trying to get it, trying to milk as much capacity out as they could, okay? So that's where I was seeing it, and that's where, kind of I got to Don and then connected with Susan on this. So her work, she was looking at different types of configurations. So her test, she had 4 test series. First test series was a single anchor, and this was connected to an angle, and this angle was a 3x3 by 5/16, and in this case it was only 5 inches here. She looked at her second series, which she had 2 anchors, and those were at 5 inches, and she was using a constant diameter stud of a 1/2 inch, and the studs were 4 inches long. The third test series she looked at and said, okay, let's take this, now that the CCD model is coming out, this was 2007, and it was starting to get adopted into the United States, well, what happens now if I take that and I open that up a little bit? So she opened that up, and now instead of 5 inches, she's looking at 2 anchors at 9 inches. And then we were also kind of in the realm of, okay, what happens if we put reinforcing in there, okay? Supplemental or anchorage reinforcement. In this case, she was looking at anchorage or a supplemental reinforcement, such that if you had this at a corner and maybe you had the top mat here, do you get any benefit from that reinforcement being close to that stud there? This was the second series with the 5-inch spacing, but in this case we had the horizontal reinforcement. So what did we find out? This was her test setup. She had some 4-foot by 8-foot slabs that were 8 inches thick. And what she did here is to maximize the room on the slab, she put in the corner anchors here in the interior. So she kind of created the edge condition on the interior here, but it was continuous in the other direction. So she didn't have any corners and what have you. Welded on a plate to each one of these discrete angles, and then she had a clevis arrangement here, and then the load frame and the load cell, and they would pull up. So they were testing these upwards in tension, okay? Oops, boom. This is a test plan matrix. We had 4 test series. Number of anchors, we had 1, and everything else had 2. 1/2 inch, 4-inch stud length. These were constants here, 3x3 by 5/16. The angle lengths were different with the stud spacings. The only one was test series 4 that had the number 3 bar, and we had 4 tests in each series. Some other constants, the concrete strength was about 5,000. Conventional ready-mix concrete, 3/8 of it or 3/4 of an inch maximum aggregate size, and the angle strength, it really didn't matter, but it was A36 angle stock. This is pretty constant. So let's look at some of the breakout failures. So this is a single anchor, and boy, when you look at the breakout right here, kind of looks like our nice CCD model, doesn't it? Even though it's at an angle, it looks nice here, and you can kind of see here. Here's your the imprint of the stud, and you can see the breakout right here. And you also, if you look at it the front ways, you see the typical breakout on the side. You look at a 2 stud, kind of spreads that out, your failure mode, and you can see here the 2 studs right there, in the piece that came out, and you can see the imprints right here, and just kind of looks like any other test that we see when the studs would be normal to the surface. For the case where she had 2 studs with horizontal reinforcement, we have the 5 inches here. You can see the studs here, and you can see the failure plane in this case just kind of went right by the reinforcing bar. Didn't really do much for her, okay? It was actually kind of a crack former, okay, if anything. So it's like it was cracking and found the steel. It's like, I think I'm going to crack there too, okay? So it really didn't help that much with respect to that. So this just shows the failure results for test series 1 and the failure loads. And you can see they're pretty doggone close. They're right congregated around either 5 or 6 kips. Real good repetitiveness, all concrete breakout failures. So series 2, again, failure loads real tight here for the second one. And I will mention here too, we added the 4D test because the reinforcing bar really didn't do anything. So we decided, let's just bring that into this one. And because we got kind of a similar breakout on that, and also the failure load was really tight within this group here. Series 3, we're going a little higher, 11 to 12, and in this case we had concrete breakout, but we also had a stud weld failure. Sometimes happens when you have stud testing. 4. We had a little problem, or she had a little problems here with some honeycombing and with a real low test here. This one, the 4D one, we actually put that into the other series. And this one right here, we've got concrete cone breakout failure, 10 or 11 kips right here. So we were able to get about the same level of load as we were with the test series 2. So let's look at, so how are you going to look at these? So because this angle is right here and we're pulling up on it, are you going to use the tension model or are you going to use the shear model? Which one works best? Okay? And that was kind of the goal here was, okay, we've got this. What is the more appropriate model for this? Or is there an appropriate model? Does the CCD work? And here was if we were to use it for shear, this is a way you would look at the breakout for shear here, okay? So with that, these are the test results. We have the ultimate failure load, and here's the test letter in the series. And you can see the single anchors right here in the first blue. You can see we're getting anywhere from 5 to 6 kips or something like that. When we have the 2 studs, we are right in the 8 to 9 range. But what's interesting too, when you get to the green here, which is about twice the spacing of the single stud here, so you got your single stud, and this is twice the HEF value, you're starting to see almost twice the capacity, okay? You're spreading out enough that the interference between the studs is becoming nil, okay? And you can see from the last set here, oops, wrong button, that here we've got the breakouts with the steel, and those were actually close to the ones with the 9-inch, but really didn't help all that much. So we looked at the 2 ways of looking at this, with the shear model or the tension model. And with the average test predicted with the CCD, you can see the tension model values of demand to capacity and the shear. It looks like the tension model is a little bit better, but you can see here too, just a little bit better with the COVs, the coefficient of variations. So the tension model is working a little bit better on that. Now, might mention too that when we're looking at this, when we're looking at the HEF, we're actually we modified the HEF to look at the projected length of it. So we weren't looking at the full stud, we were actually looking at the projected length. So it would have been the length times 0.707, okay? So we're modifying that a little bit. These are the ratios then with the CCD as tension, and we find out that the tension model is a pretty good predictor of this, okay, with that modification. But as Neal is always, Don will attest, Neal's always looking for a simpler way to doing things, okay? Because sometimes, no offense, Rolf, but the CCD model can be a little cumbersome, especially if you're doing hand calcs, okay? like I do sometimes, okay? So you kind of look for a simplification on this. Is simplification possible? Well, yeah, I think so. Because when you really look at this, what really are your variables? Your variables are going to be what is your HEF, because you're only varying the stud length here, okay? Likewise, you know, most of the cases you're going to be putting this on a 45-degree angle, so that's constant. Another variable is going to be your stud spacing in and out of the page or in and out of the slide, okay? So you really only have two variables, okay? What are constants here with this type of angle? Well, right at the edge, you're going to have your edge distance is going to be constant. It's always going to be the same. Likewise, your eccentricity is always going to be the same when you look at it in a tension model. And here's your effective stud length when I talked about that, okay? So it's going to be the length of the stud minus the head plus a little bit of the angle right there, okay? So that's going to be constant. You know, that's going to be based on the length of the stud. So everything else is constant here, okay? You just have two variables. And with that, we did some analysis on it, and we're able to look at those and really boil this down to a model where it is based on the effective embedment depth, and then we have a spacing factor, and this spacing factor is based on the spacing of the studs, but it's 3 times the effective embedment depth. And obviously you want that less than the number of studs, okay? We also looked at, I believe with the analysis we did, we have 1.0 for uncracked concrete and 0.8 for cracked concrete on this. Oops, boom. With that, conclusions on this, you know, pretty simple research project, and that was use a non-standard assumption, and that is an effective embedment depth, and that effective embedment depth is a projected length. Single and 2 anchor strength can be well predicted by CCD. And we can simplify that design because your edge distance and eccentricity are defined. And you really have just 2 variables, okay? Now, I'm trying to make this very simple, but it's not that simple, right? When you're really looking at this, there's some further research and further thoughts on this, okay? So a lot of times, when you're looking at these are armoring some sort of a corner, okay? Well, it's not going to be discrete angles like I was looking at for a balcony edge, okay? It might be a real long angle, okay, or several feet. So Susan's work really just looked at discrete angles. And I think for right now, the recommendation might be if you space your studs greater than 3 times the effective embedment depth of a stud, it's not that far, you pretty much avoid any type of overlap. And you're going to get the single stud capacity times the number of studs, okay? Another thing to be concerned about too is, do you really have to worry about the angle thickness of this or the stiffness of the stud? Her work, she looked at 1, and because they were discrete angles, that really didn't come into play. But if you have a continuous angle and you're trying to distribute the load, obviously you're going to have to worry about that. And another thing to worry about too is, and this is something we have in for shear lugs, in the anchorage provisions, is you might have to put weep holes or vent holes in the horizontal leg here to prevent honeycombing or problems with concrete consolidation underneath that angle. Because a lot of times, you know, we're looking at a model where, you know, we're pulling here and this is effective, but you want to make sure in case this thing wants to act kind of in shearish that you're well consolidated around there and you don't have any issues, okay? Because if you have voiding in there, it could be, you could start bending your angle, okay? Because you don't have that consolidation and you don't have that good behavior. So, with that, I'll take any questions. And if I can't answer them, I'll give it to Don. So.